Okay, I'm going to introduce Andrew McPherson, who's going to talk about digital content creation using LLVM. Andrew.
Hi, my name's Andrew. I work for a company called Fabric Software, and we have a product called FabricEngine and our own custom JIT language based on LLVM called KL. And I'm just going to talk a little bit about what it is that we do and how we do it today. So first, I'll give you a little overview of what FabricEngine is, just so you have an idea. And then I'm going to go into some more specific use cases of how we use LLVM, specifically the MC JIT backend, and then some other kind of benefits we get from LLVM as well. And then finally, just really briefly at the end, a couple of kind of sub-projects of LLVM that we're interested in moving forward. So FabricEngine is a digital content creation framework. There are a lot of digital content creation applications on the market, and some of you guys might be familiar with some, like Maya, say Softimage, 3D Studio Max, that kind of thing. We don't develop an application. We develop a framework for others to build applications, because what we found is a lot of the studios and the users out there who are working with these have enough knowledge in-house to know what they need, and what they need is not something that can necessarily be bought off the shelf. So that said, we do allow writing applications with our framework, and specifically the easiest way is with our Python API and a PySide framework. So here's an example of a FabricEngine application built using our PySide framework. This is just a demo app that we ship with our stuff to give users an example of what they might want to do. So this one has a bunch of assets on screen. There are some cows and a house and a teapot, and it's doing some kind of raycasting operation with a little manipulator that you can see in the middle there. That's a sample of an application. The other thing we do is we provide integrations for existing digital content creation tools, because a lot of the people who are using the existing software, like Maya or Softimage, aren't quite ready to completely throw that away and move somewhere else. However, they would like to take advantage of some of the nice benefits that we provide with FabricEngine. So we have something we call Splice, and Splice is a collection of plugins for these existing applications that lets users stay within the framework that they're comfortable with, but still take advantage of some of the things we provide. So here's an example of what one of those looks like, and this is our Splice plugin for Autodesk Maya. And you'll see on the right side of the screen, there is the Fabric Splice IDE, and this is where users can directly on the fly modify their KL code, which is our JIT language, and affect what's happening in the viewport. So in this example, the KL code within the little IDE on the side is being used to generate this procedural geometry, some kind of squiggly circles that you see in the middle there. And finally, just to mention, this is not just a good idea, it's a good idea that's been validated. There are some studios who are using our software right now in their pipelines, such as the Moving Picture Company and Hybrid. Okay, so why does FabricEngine exist then? If we have these tools out there that people like, and people are using these tools, what are we doing in there? Well, the problem is with a lot of these tools that they're a bit older, they're fairly monolithic, and they were built at a time when kind of the default architecture was single core for a lot of the systems. I mean, some of them you're talking maybe 20 years old. Now, they have evolved over time, of course, but there are still kind of big portions of the application that weren't really designed for modern architectures. The other problem is that they are closed, and they're not very configurable in many cases. So you have this big application, and it can do most of what you want, but there are tiny little parts of it that aren't doing exactly what you'd like, and you're unable to change them, because it's a closed source app, and you simply don't have access. Now, they do all provide some kind of API to have access to portions of what they're doing. But the trouble there is that writing plugins is either difficult, if they're writing in C++, or slow, in terms of performance, I mean, if writing in Python. And the other thing is that a lot of the people who would be writing these applications are not necessarily programmers by training. They would be kind of your technical directors, your technical artists, and they can be very good programmers, but their background isn't in that, and it's not necessarily their core competency, and it's not what they want to focus on. So writing C++ plugins is not something that most people want to do, but they're forced into it sometimes. So you end up with development in some of these studios being held back by limitations in the software they're using. So here's a little mini overview of kind of what FabricEngine does provide. So here's some little demo applications also written using our framework. So the core of what we provide is this KL language and a dependency graph. And the dependency graph is staged from a host language. And the two main host languages we use right now are Python and C++. Now, those could be any other language, but those are the two in use with the people we work with. So these host languages are used to kind of stage and set up your KL environment, to bind your data from your application into your KL operators, and then to set things in motion when things are good to go. Within the KL language, we also provide some kind of simple multi-threading paradigms. So one of the goals of KL is to kind of limit the scope of what users can do, which sounds like maybe a bad idea, but when you're talking about making things simple for users, you want to keep the paradigms that they're able to have access to fairly simple. So I'll show you a little example in a minute, but simple multi-threading paradigms are important for us. We're also fully cross-platform. The majority of our stuff happens in Windows and Linux, but we also support OS X completely as well. And when I say that, I mean our standalone platform as well as our splice plugins for different applications. And one of the nice things is that because all of the code that's really driving execution when you're talking about this digital content stuff is written in KL, you suddenly get this magic thing that happens, and that your code is portable between different applications. So if there's a company using, say, Softimage and Maya in their pipeline, any code that they write in KL suddenly becomes portable between the two. So code to do rigging or whatever it might be isn't just used in one place, and that is an issue at some of these, with some of these customers. Okay, so specifically, how does KL help in here? KL, the main thing it aims to provide is the ease of Python with the performance of threaded C++. And that's the kind of claim when you go into a studio and say this, they say that can't be. But I think in an LLVM conference, you understand that we're just using LLVM in the background, we're running all the optimization passes on our IR, and we can effectively get the performance of threaded C++ code. We also have the benefit of, like I mentioned earlier, write once, use anywhere. So your KL code becomes portable from within existing applications or into standalone. We also aim to provide something that is crash-free and updatable on the fly. So what I mean by that is when someone is using their DCC application, their content creation application, and they have their KL IDE within it, we don't want a coding error to take down the whole app. We want users who are able to experiment with the code, see what they can get out of it, and not crash the app in the process. And of course, updatable on the fly, meaning code, 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 compile and run, code, 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 compile and run, although for them, they don't see the compile step. For them, it's just code, 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 run, and things run and things happen. We support extensions like many other languages, so you can connect to another library in the background that you want to do, if it's a physics library, say, or some kind of content library to load data from the disk, whatever that may be. And here's something else that's very exciting to users, is that we provide target selection at runtime for supported GPU targets. So you write your KL code once, and you can run it on CPU or supported GPUs, and I'll come back to that in a bit. I'm not going to go over syntax of KL, or this is not a demo about learning KL, but just so you can see what I'm talking about, this is a tiny little KL program. You see it requiring a math library at the top. At the bottom, there's our entry operator, which is like a main. The one thing I would point out is just the initialize function. You'll see a parallel init with a bit of a funny 3 angle bracket syntax. Anyone who's done CUDA programming probably recognizes this. This is the main parallel execution paradigm that we provide to let people run multi-threaded code. And what this is saying is call the parallel init function v.size times passing it these parameters. And you'll see that parallel init function defined above. All that means is telling our scheduler, I need this run this many times, you figure out how to do that. Okay, I'll move on to the next. Okay, how does KL achieve all this wonderful stuff? Obviously, it's LLVM. So it's an MCJIT-backed language. We provide the Fabric core compiler based on MCJIT and our scheduler. That's kind of the core of what we provide at FabricEngine and the only closed part of our system. Everything else that we provide, down to our real-time rendering engine, is all written in KL code and is shipped as open code for users to play with and modify as they need to suit their specific needs. Okay, so we'll look at a few specifics here. Okay, what's important for KL? Okay, ease of use, like I said, but that's all on us. That has nothing to do with LLVM. We need to write a language that users will find easy. Next is fastest possible execution time, because that's one of our selling points, right? You're using slow, maybe Python or something else that's just not operating at full speed. We guarantee that things will run really fast if you're using FabricEngine. Next is providing a minimal memory footprint, because again, we're dealing with digital assets that can be huge, and people want to squeeze every drop of memory that they can out of their systems. So if we've got hundreds of megs being used up by our JIT engine, that's going to be an issue. And no significant startup delay. And I mean, of course, we want everything. We can't achieve all of these easily, but I'm going to talk about specifically what we do to get closer to achieving these things. So the first thing is the compilation passes in KL. KL is a pure JIT language. There is no interpretation that happens at any level. So that means automatically there is going to be some startup delay because of the fact that things need to be compiled. That said, we can't just compile them as quickly as possible because we want maximum performance. So our solution to that has been a 2-pass compilation, meaning that when we get new KL code that we have not seen before, we immediately code gen it. using the lowest possible settings on the code gen. So no aggressive code generation. We just immediately get it done and start executing that. But as soon as that's done, as soon as that compilation has completed, we kick off a separate, well, not a separate thread, we kick off a task to our scheduler to do a complete optimization pass and an aggressive code gen in the background. And when that's ready, I'll get into linking in a minute too, we swap that in place for the one that's been running slow. So what you'll see when an app comes up is it may be grinding a little bit, not as fast as you hope, but then as the seconds tick by, boom, the FPS kicks up and until things are fully optimized and everything is running smoothly. I like numbers, so I'm going to go through a few numbers in a few different ways here. This is just the first one, but this is a sample case with one of our demo apps. It's called City at Night, and it shows a few interesting things about our real-time renderer. It shows like some cars moving around, they shine lights, they cast shadows, there's motion blur on the cars, so some nice kind of features. And this application is made up of about 37,000 lines of KL, which is a 1.8 million lines of IR pre-optimization. Using a very naive approach of upfront optimization on a single thread, because what we do when people pass us KL code, as soon as we return from them giving us that code, we guarantee they can call and use it. So when I'm talking about both these cases here, I'm talking about a single thread just going straight ahead and doing full optimization and full code gen and then running, or doing no optimization, minimal code gen and running. And you can see the difference that we get there in startup time. So you're talking about 3 minutes to start this app is insane. 37 seconds is still fairly insane, but it's much better than 3 minutes. So 37 seconds to load this app initially, the very first time, by doing this background optimization is a good start. But it's not good enough, obviously. So then we get into caching. With a lot of the stuff in the KL code, we don't want to compile libraries and ship them. We want every piece of KL code to be updatable on the fly as the user wants. But with the object cache, which was introduced in MCJIT last summer, we get exactly what we need. Because a lot of what will be compiled initially on the first load of any app will be a lot of the standard libraries that we provide, or our core extensions, or other people's extensions that they've written. So we cache, in these cases, both the IR and the objects. We use a key based on a hash of the KL AST. So whenever we get KL code, we parse out the AST, we hash it, we check our cache and say, do we have something for this? If we do, we load it up. If we don't, then we do the full compilation and background optimization pass. And we have a little hack in there as well, in that we don't actually cache the full IR. And I'll show you what I mean by that. We cache what we call an IR stub. I don't know if you can see this, but I'll explain it anyway. At the very top is a piece of KL code, and it's that initialize function that I showed you a little bit earlier. What specifically it's doing doesn't really matter, but if you see in the second piece, those are the first few lines of IR that are generated for that function. And then in the last one, you'll see the IR that we actually cache. So in there, all it is the function, a single basic block, and an unreachable. So what's that about? Well, prior to LLVM 3.4, you could add modules to your MCJIT execution engine, but you couldn't remove them when compilation was done. So that meant any memory being taken up by modules was taken up by those modules for the whole run of whatever you were doing with that stuff, until you killed the engine. By doing this, we dramatically reduce the amount of memory being used by modules. And the way MCJIT works is that when it loads a piece of IR and you say compile this, it just checks, does the function have a body, which in this case it does, an unreachable, and then it immediately code gens. And then the cache kicks in. And we intercept that in the cache, hand it a fully compiled thing, and we're good to go. So this gives us lower memory use and faster startup, because it doesn't need to parse this IR. And it's not a huge difference, but we're talking on the order of a couple of seconds spent parsing IR that will never be used. So this is what we've been doing with stubbing our IR in the cache. And you'll see this is getting towards a more acceptable startup time. And this would be more kind of the general case startup time for a FabricEngine app. So the first time you run, there's going to be a lot of compilation happening. All the threads are going to grind. You're going to dump a bunch of stuff to the cache. And then next time it kicks up, it'll be loading from the cache. And we're talking closer to 4 seconds to load an app, which is getting, that's not too bad. I mean, and the nice thing here too, for us the nice thing, is that most of this is our fault. So we like that because we can fix our own code. If this 4 seconds for us is spent parsing the KLAST and doing other stuff, that's good for us because we are very much users of LLVM, not so much diggers in the core of LLVM. Not that we are avoiding it, but we are a fairly small company, so we focus on using what's there and available. Okay, linking is another issue that it's been discussed a few times on the mailing list, but with MCJIT. I'm not saying this is the be-all and end-all way, but I'll just go over how we do our linking. So when I talk about extensions, like the math extension I mentioned, where you require math, all of these extensions export their functions and their methods on their objects. And in the core, when we're doing linking, so when we get a new object coming up and it's calling functions in these extensions, the core is binding in a swappable pointer. So it's not binding in the function directly, and we do that for two reasons. We do that, one, for the optimization passes that I mentioned. So we bind in this function pointer that gets swapped whenever we want to change the function code, and that lets us update the function code due to user changes or due to our compilation passes. The trouble with this is, of course, that's going to slow things down. So you do not want to do this for functions that are tiny. You don't want to do this for functions that are called a lot, because you're talking about jumping every function through an indirect pointer. So our solution to this is an explicit inline modifier in functions. And what this means is that the user must specify which KL functions he or she wants to be available for inlining in the user code. I'll show you just a little bit what that looks like. I mean, it's very simple, and this is the kind of function you'd generally be talking about. Very small functions doing fairly simple math of complex types or comparisons or stuff like that. These are marked with an inline at the beginning instead of a function. A few more numbers just to show you what I'm talking about. So using a really stupid inline everything naive approach where everything is inline. So whenever you require an extension into your code, it dumps the entire extension in and lets LLVM sort it out, which is nice. It'll result in the fastest possible code because LLVM will optimize it correctly. However, you see the startup time is massive, right? So we can't do that. And then using the second naive approach of inlining absolutely nothing, just letting everything happen, let the linking happen and let everything go through these indirect pointers. This may not look like a big change, and it's not. In this case, it's maybe about a 20% drop in performance, but it's still not something that we would want. And it's going to depend on what exactly you're doing in your application, how big this drop is. But using the selective use of inline, meaning the extension developer who is writing the extension says, these should probably be inlined, we achieve a slightly higher startup time and the exact same frames per second in the end. So this is how we're handling linking in our particular case. I'm going to touch on memory use just a little bit. Like I said, we want minimal memory use once compilation is complete. LLVM 3.4 actually added the ability to add and remove modules on the MCJIT engine, which this is a testament to how well MCJIT, I think, is following what we need. I mean, object cache came in exactly as we needed it, and this kind of came in at a point where we were thinking, what are we going to do with memory use? So this is quite handy. The trouble is we still do need multiple execution engines, and the execution engines do take up memory that we would rather not be taken up. And the reason we need multiple is because we want to do this background optimization. And there is locking within the engines, so you can't optimize or you can't compile more than one module at the same time, which is totally fair. So I'll show you just a few little things here about memory use. This is another demo. It's a crowd simulation. It's got tens of thousands of agents circling around and interacting with each other in some way. This is while loading this particular demo from the object cache. The first thing you'll see is loading the full IR of every module. So not the stub, but the real IR that was optimized, and then not removing the module. So these first two are what we had to do in LLVM 3.3 and before. So you'll see, using the full module and not removing it, 800 megs. That's big. That's a whole lot of memory there. Just making the tiny change of switching to those stubs, where everything's non-reachable inside the functions, we suddenly drop down to 428 megs. So that's already a huge savings, and that's what we were happy about before. But then in LLVM 3.4 now, we can remove the module completely, which is nice. However, there's still, okay, and let me just say, RSS is maybe not an absolutely perfect measure of memory. But what I'm looking at here is not so much the numbers, but the differences when things change. We've also done profiling with Valgrind Massive, and we see very similar numbers there. Once we can remove the module, with the full IR or the stub IR, we're down to 367, 356. But what's interesting there, you'll see there is still a small difference between how much memory is left over after loading the full IR versus loading the stub. So there's no reason for us to switch away from using the stub IR in our cache, even though we probably could at this point. And then the last number is what we would get is if everything could be just crammed into a single execution engine. And that's starting to look really nice. And of that 300, that's really mostly our fault at this point, and that's nice. OK, I'm going to come back to the GPU compute side of stuff. So with our KL code, it can be run today on the CPU or the GPU. We support AMD HSA hardware and NVIDIA CUDA 6 hardware. with shared memory via the driver. So the real thing that we need here is we do not want to worry about where that memory has to live, because that's really hard. If we need to guess and know like when to transfer memory to the from CPU memory to GPU memory, the scope of the problem becomes massive. So if we can rely on AMD HSA hardware, where the memory is shared already, or NVIDIA hardware, where their driver is going to manage that transparently for us, this suddenly becomes a much more manageable problem. So right now we do support both of those bits of hardware, and we've seen speedups in our demos, in our kind of testing, where it could be 10 times faster or more. And what's nice about this is that this is not someone coding like an algorithm specifically suited to the GPU. This is taking an existing algorithm and simply running it on the GPU to see what's it going to do there, which is really what we're targeting. I mean, we want people to be able to experiment with this stuff and see what works there. And I mean, obviously, there are certain algorithms that are simply not suited to the GPU, stuff with lots of branching or lots of indirect memory access or stuff like that. However, there is a large class of algorithms that are very well suited to the GPU. And we want to make it very easy for users who are not supremely technical to try it out and see what works there. And for more technical users, they can craft their algorithms that they know will run very well there. And that should be easy for everyone. Some more numbers, just because I like them. Here's another demo of ours. It's a silly demo. It's just built to show off kind of the efficiency of our scheduler. And it does a Mandelbrot set to varying levels of depth and complexity. And we run this on standard desktop hardware. I'll use in quotation marks, because this is an NVIDIA Quadro K5000 is not standard for most, but for our users, that would be a fairly standard kind of GPU hardware. So you'll see a fairly powerful CPU, Intel Core i7, get about 3.7 frames per second in this demo, and then simply clicking the button saying run this on GPU, and that's it. Nothing else changes. It jumps to 23.5 using an NVIDIA Quadro K5000 in this particular test case that I did here. So that's really nice. And let me show you what that looks like in the KL code. So in the KL code, this is the compute pixels call, which is part of that Mandelbrot demo. Takes a bunch of parameters. This is invoked through a bunch of other code, but I just want to focus on this one part here. You'll see the compute pixel call. It's the same triple angle bracket syntax that I showed you earlier. But the difference is this one is taking an @ symbol, and it's taking a Boolean, and that Boolean is settable at runtime. And if that Boolean is true, the core scheduler will say, I'm going to try to run this on the GPU. And it's as simple as that. So a user can simply write their parallel execution operator, tell it how many times to run, and then if they have a supported piece of hardware, say GPU or no GPU, and the scheduler will take care of the rest. Last little thing to touch on is debugging. So this is not MCJIT specific, but this is something where we are benefiting hugely from what exists in LLVM. And we're using LLVM's DI builder to put dwarf info into our KL code. And this is also working today, and this is very exciting. And in fact, last month, we, along with one of the guys from the Julia project, Kino Fisher, we added JIT support to LLDB. And this is working now, and it's in the head of LLDB at this point. So this means you can pull up LLDB and connect it to a running Maya process where the Fabric Splice plugin is running, and debug your KL code, and step through the lines, and you'll step, in Linux at least, step cleanly out of the C into the KL and back again. And this is really powerful. And it includes the ability to step into our extensions, which may be written in C++. If they have debug info, we get debug info in the whole spectrum of our code, from the C++ through the KL, back into the C++, if that's the way it is. And we also provide a front end that we've written, because again, a lot of our users are not necessarily used to a command line GDB or LLDB program. So we have a Python plus PySide front end. Small example of it here. This is debugging another one of our demos with some cars. You'll see it looks a little bit like Visual Studio, because we do love the Studio debugger, and we're trying to make something that looks and feels a little bit like that. So you've got your variables at the top, you've got your code in the middle, threads, backtraces, breakpoints, all of that stuff is in there. And this also works. And this particular piece is also an open source project that just sits in our GitHub account. Anyone is free to check it out if you do debugging of any kind, whether with JIT or without JIT. Okay, looking ahead, this will just take a couple of minutes. Some interesting stuff for us would be further reducing the MCJIT memory footprint. This is not something that's killing us at all, but any little bit here would be really nice. One that it's not actually on this list, but I was thinking of as I was listening to people speaking earlier today, speeding up code gen is also something we would love. We don't really have the resources to put into that ourselves, but if someone were to put in a faster, even a really crappy code gen, but a faster one, we would love that, and we'd be all over that right away. Better error handling in out-of-memory scenarios is another one, because again, like a lot of the users that we work with deal with massive digital assets. They would much rather an error message saying, stop what you're doing, than to have their app go down. So I know there's been a little discussion on the list about this stuff recently too. So that's just an area that we are interested in. The others are LLDB and Clang on Windows, which is why it was very cool to listen to the talk just before this one. But LLDB on Windows is something else that we're very interested in. So we have LLDB working great in Linux. It works great in OS X. I mean, it's the default OS X debugger, so it's working fine on OS X as well. And we would really like it to be able to work in Windows, because then we can debug KL code in a Windows application, which is exciting. And Clang kind of ties into that, because and it's good that people are asking about debug info and how debugging would work with Clang CL, because then that's really nice. Because what we're aiming for initially with LLDB on Windows is the ability just to debug the JIT KL code. Once you step out of that, you're in no man's land. But if that didn't have to be the case, that would be great. So that's what we're kind of looking at Clang on Windows for. And then a question mark around GPU debugging, because I don't know what that would look like. It's going to require vendor support, but could LLDB play a role there? Maybe. It's something we're very interested in any case. So if anyone else has any ideas or anything there, that would be cool. And that's it. So thanks very much.
Questions? Yeah, that's better. Questions? Okay.
Cheers. So the debugger looks really interesting. Is that a standalone tool? Can it be used separately?
Yeah, absolutely. It's just all it is a Python script. It uses the trunk LLDB Python library, and it bases on the UI is PySide, and it sits on it's completely open source.
Oh, great. And have you tried that? You haven't tried it on Windows yet?
No, well, it doesn't work on Windows simply because LLDB doesn't really work on Windows.
Okay, yeah. What's the toolkit? Is it
the toolkit for
the GUI?
PySide.
Okay, right.
Yeah.
Okay, nice.
Yeah.
Looks really nice.
Just to answer the guy there, if it's a remote target you're debugging with LLDB, it'll work perfectly.
Yeah, sorry.
Yeah, so
that's right.
Yeah, I think I'll come down and have a discussion with you later on about this LLDB stuff.
Okay.
Yeah, I've seen you in the mailing list quite a bit.
Any more questions for anyone?
I have a couple of questions. I'm wondering how you do the GPU support. Do you use a LLVM backend for the GPUs? Or?
Yeah. So I mean, we just have our IR that we generate, and I mean, the IR's got to be tweaked a little bit based on CPU, GPU, with address space info and that kind of thing. But then we just use the vendor backend, whether it's AMD or NVIDIA, and let them generate the machine code.
Okay. The other question is, KL appears to be a kind of imperative language. Do you do like memory allocation and stuff in there?
Yes. There are different types of, different types. I mean, there's objects and structs and different types of arrays, and it's all very open and accessible to the user. I mean, again, the idea is that none of this should be mysterious, and it is documented how exactly memory is used by each of these things. I mean, some live on the stack, some live on the heap, and the knowledge is not hidden.
Okay. And do you garbage collect it, or is it?
No, it's reference counted.
Okay. Thanks.
Yeah.
I've got one. You said you use the GPU vendor backends. Do you JIT with those as well?
Do we JIT with?
Are you still using JIT? You're still using MC JIT for those backends? Or is that just for the x86 target that you're...
To be honest, I would have to check. I didn't do the GPU support. That's our other head developer, Peter Zion. I would have to check with him specifically. I'm not sure offhand.
Okay. Any more from anyone else? Okay, let's thank Andrew for his great talk.